We'll move on to 3D geometry. So last class we were playing with Pythagorean Theorem. We just have a couple more things to do with that. So Pythagorean Theorem is related to right triangles. We looked at a little bit of the geometry of the Pythagorean Theorem and why it should be true. So today we're just going to play a little bit more of things you can do with the Pythagorean Theorem. So given a right triangle, let's say that one right there, that's a right angle. Call that length A and that length B. Anybody remember what A and B are called from last time?
Legs.
They're called the legs of the triangle. Yeah. And A and B represent the lengths of those legs. And we have the side opposite the right angle. What's that side called? Hypotenuse. Yeah. So we usually label that one C. Switch colors. And what was discovered a long time ago is that if you measure the legs and you square them, and then you add up those squares, that's always the same thing as the square of the length of the long side. So the sum of the squares of the legs is the square of the hypotenuse. Famous triangle that meets this description is a 3, 4, 5 triangle. So if you take sides of length 3, 4, and 5 and you stick them together, it has to make a right triangle. Check. 3 squared plus 4 squared, does it really equal 5 squared? 9 and 16 is what? 25, which matches. Okay. When whole numbers happen to fit in nicely in a Pythagorean theorem, the 3 whole numbers you get are called Pythagorean triplets. So this is the smallest triple of numbers that makes a right triangle. Whole numbers. Mostly right triangles don't involve whole numbers, they involve square roots. Okay. So this is 3, 4, 5 is a Pythagorean triple. And we played around with that in one of the activities last week. Pythagorean triple. So I think we ended up at the end of class last time, we found a couple of triples. So some other things we can do with the Pythagorean theorem. If we use it with some algebra stuff, like consider the graphing that you once did. We haven't done much here. We have an x-axis, we have a y-axis. So let's suppose I have the point -2, -1. And then let's get the point 3, 2. Couple of things I can do once I have that point. I can connect the dots. And then I can also think about it as the XY coordinate system. I have to move a certain horizontal distance to get there and a certain vertical distance to get over there. So I can build a right triangle based on any pair of points. So what can you tell me about this right triangle? What do you know just by looking at it? Besides this right. Anything? You describe to me how to get from one point to another?
Oh, the slope.
Yeah, slope, right? That's in there, right? So that's kind of how to get from one point to another. So give me some numbers related to the slope here.
Price over run.
Okay. So what's the run here?
The run is it's -2 and 3, so it's 5.
Yeah, so to get from here horizontally over to that way, I got to move 5 units to the right. And then the rise would be 3 units. Okay. So once I look at those 2 points in terms of horizontal and vertical movements, that is going to make a connection to this diagonal movement. How can I connect those vertical and horizontal movements to the diagonal movement? Thoughts?
Squaring both the lengths should give you the square of the.
Yeah, the Pythagorean theorem is living right here. So if I wanted to know how long this length is right here, well, I know the Pythagorean theorem, I know the length of each leg, I can then come up here and say, oh, all right, that length right there has to be related to 5 squared plus 3 squared. Pythagorean theorem says if that's a right angle, if you square the lengths of the legs and add them up, that's got to be the length of the long side. Call it C. At least C squared. All right, so 5 squared is what? 25. And 3 squared, 9. 9 and 25 is 34. So I'm looking for some number whose square is 34. Now that's not as easy as like if I'm looking for some number whose square is 25, you would tell me the answer is 5, because 25 is a perfect square. Is 34 a perfect square? No. So the only way we can describe that length right there is to say, well, if you take the square root of 34, then you'll get that length right there. So the Pythagorean theorem allowed us to find the distance between these 2 points. So that's the big thing I'm putting out here. So the distance between points is an application of the Pythagorean theorem. So I'm going to give you 2 points. I want you to repeat this and figure out how far apart the points are from. Okay. So just based on the Pythagorean theorem, I can plot the points, find the rise and the run, make that right triangle, and then move. Got it. So your 2 points are going to be 1, 2, and how about 5, 7. So find the distance between those 2 points in a similar way to what I just did. What do you think the length is?
Square root of 41.
Square root of 41. Nice. That's not that bad, is it? Okay, so I'm just going to make it a little more exciting by using variables instead of numbers. So, brace yourselves. I think this is way more fun, but variables are nice too. Have their place in the books. So instead of calling the points 1, 2, or 5, 7, I'm just going to say, well, we've got this first point somewhere over here, and we've got this second point somewhere over here. Now the points can be any orientation to each other. It doesn't matter whether one's to the upper right, or lower left, or upper left. That doesn't matter. If I call this the first point, then I would say we could refer to it as x1, comma y1. First x value, first y value. And then this one over here, we'll call second x value, second y value. That's my second point. And I want to use the process we just used to come up with a way to get a formula for distance between 2 points. So what was the first step in our process from before?
Find the distance, or find like the
horizontal and vertical distance, right?
Yeah.
So like think of it like city streets. We have to move horizontally to get from this x value to whatever that x value is, and then we move vertically from this lower y value to this upper y value. And that's going to give us our right triangle. Okay. So down here, that's my x1. Down here, this is whatever x2 is. Before it was 1 and 5. Here is my first y value. Here is my second y value. Okay, so we drew the picture to help us visualize it. Then what do we do next? We found those distances, right? How do I find that horizontal distance?
x1 minus x2.
We just did a subtraction. Yeah, so, and I would do it the other way though. So I'm going to call it x2 minus x1, because then the sign, I get the sign right. But it turns out it doesn't really matter if I get the sign right. Does anybody know why?
Because the squares.
Because then I'm squaring it. Yeah, I'm squaring it and I lose the negative. So if I mix up the order, it turns out here it's no big whoop. With slope, it is a big deal, because then we get the direction wrong. So what's the distance on this vertical side of the triangle?
y2 minus y1.
Yeah, it would be this number minus that number. So that'd be y2 minus y1. So I'm going to call, instead of calling that C up here, now I'm going to call it D for distance instead of calling it C. So the Pythagorean theorem says that that long side squared should be equal to this leg. So that leg would be x2 minus x1. If I'm going to square that, I got to put it in parentheses because I've got to subtract order of operations, right? Subtract first, then square. What should I do next? Plus, yeah. Yeah, plus my y2 minus y1, whatever that ends up being. I got to do the subtraction and then square, right? That was our process from before. And then, well, that's the Pythagorean theorem, right? There's one more step to turn the Pythagorean theorem into distance. What is it?
Square root it all.
Yeah, if I take the square root of both sides, that kind of cleans things up. So then finally I can say, all right, the distance, ooh, I didn't freak out. I mean, it's because I'm really excited about the Pythagorean theorem. B would then be the square root of this crazy stuff right here. So we've got two different ways to look at this problem. Both of them depend on the Pythagorean theorem. When we abstract it with variables like this, we end up with this cute formula. We may argue about whether it's cute or not. I think it's cute. We also have this process. Okay? So what I want you to think about for a moment are the pros and cons of the process and the formula. Just pause for a minute. Why might one be better or worse than the other? Just think about that. Write down at least two ideas about that. The yellow thing I circled has a fancy name. It's called the distance formula. Not as cool as the Pythagorean formula, theorem. Thank you. And I've got a couple of thoughts about why one versus the other. If you like one version better, try to be the other side and try and argue for the other formula, or the other process. Is that what was rattling over there?
I was
I was wondering where it was coming from. Okay, so something in the air is vibrating the wall, which is vibrating the table. Good troubleshooting. All right, anybody want to make a comment about one versus the other? Let's start us off.
Is the formula easier if the numbers are bigger?
Formula might be easier if the numbers are bigger. Yeah, it could be. Test that idea out. Because then you don't have to worry about trying to draw it, because the numbers might be too big to scary to draw perhaps. Okay.
That's kind of what I had too, hypothetical points in space.
Okay.
The Pythagorean theorem, it works better on the, or it doesn't work as good on the graph if the lines aren't all like on the same rise and run, for, like the x values of the a wouldn't be the same and the y values of the b wouldn't be the same. I don't know if that makes any sense. It makes sense in my head.
It turns out you can always make a right triangle, no matter
Yeah.
where the points are. So I'm not sure I get your points. Say it again.
Because like if you have a right triangle that's like off kilter, and so the lines aren't perfectly straight up and
Yeah,
down and side to side.
so here we're not starting off with a right triangle, we're just starting off with 2 points.
Yeah.
And the 2 points are always going to make a right triangle where this is parallel to the x-axis and that's parallel to the y.
Okay.
Yeah, so that's always going to be the case when we do it that way.
What if the points are between?
Like if there's like decimals or fractions and
Yeah, it
stuff.
would be easier to do the distance because it's just basic algebra rather than trying to so.
Yeah. Yeah. So here's one thought I had on Wednesdays. I'm much more creative and I like drawing pictures, and so that method works better for me. On Tuesdays, I'm way more analytical and I like something that's more efficient, and that's more efficient because I don't have to draw a picture. And it could be just the personality type. Some people just like memorizing formulas. They say, I don't want to know why, just give me the formula and I'm done. There's the formula, you're done. You just got to remember when to use it. Bottom line is, it comes from the Pythagorean theorem, which is kind of cool. So they're both good. They both have their different values. For me, if I want to be accurate about something, I'm going to do it both ways. I'm going to draw the picture, I'm going to use the formula and make sure they match. Okay? Because sometimes accuracy really matters. Okay? If I'm working on building a bridge, I don't want one half to miss the other half. Okay? So I want to find ways to double check myself. Yeah, so there's no perfect answer to this question I asked there. They're both good methods. Pythagorean theorem leads to the distance formula, and a lot of people just like to memorize that. Okay. So I'm just going to give you another set of numbers. You decide how you want to do it, and we'll see what happens. Let's see the other point. What's the distance between those points? Interesting. as far as I can get on a calculator. Well, I could go farther, but I don't wish to. I make a mistake?
256 minus 125 is 131.
Oh, shit. Shoot, excuse me. It is 131. You are correct. All right, let's fix that. Oops, switch to red. So that's a 3. All right. Seven, 161. $26, 186. It's slightly bigger square root. 161.8. How's that look? Better? Boom. So just for fun, I'd like you to try and make a rough sketch of this too.
But you got that.
So there's my rough sketch of it. What did we get? 161-ish? 162?
161.8.
I'm just going to call it 162. So one nice thing about the picture is it tells me if the numbers seem reasonable. Does it seem reasonable that if this is about 100 and that's about 130, that should be about 160? It seems reasonable. Yeah, so it gives me an idea if the number I calculated is actually in the ballpark. What if this came out to be 100? Would I have a problem? It'd be too short to make a right triangle. Would be a problem. If it came out to be 10, if it came out to be 1,000, I could see in the picture, whoa, that's not right. Now, my little mistake earlier where I had my subtraction was a little bit off in my head, I wouldn't have caught that mistake because I would have said, 154, it's close enough. It looks in the ballpark. But if I redid the subtraction, I would have caught it in the picture. So are there some points we might be given that are just really painful to draw? Sure, there definitely are. Right, and so that's an argument for one is better. But they both are good and bad. Okay, so next cool thing about the Pythagorean theorem. I think we'll be okay with our graph paper. I forgot to print some today. So let's take a look at a circle. And let's do a really simple circle. So here's my circle. Want to guess what the radius is? 1. Yeah, so when you draw a circle of radius 1 is called a unit circle. 1 unit is the radius. Okay. So this is a circle to the best of my artistic ability of radius 1. What's the center of my circle, do you think?
0.
0, 0. Okay, so right there, I was aiming that to be the center. So center. 0, 0 for x and y. And what I want to do is I want to see if I can come up with an equation for this circle. And to do that, I'm just going to pick a point. I'm going to pick that point right there. Now, I just kind of threw my pen as a dart in the first quadrant there, and I just randomly hit that point, sort of, kind of. I'm not really exactly sure what the x value of that point is or what the y value is. But I know that point has an x value, and it has a y value. And guess what I can do with that x value and the y value? What was that? I can make a right triangle. And one wicked cool thing about this right triangle is, what can you tell me about that side right there? Yeah, good job. Okay, it is 1 because that's the radius. All right, so I have a horizontal side to this triangle, and how long is it according to my picture? My horizontal side of the triangle. It's less than 1, okay. Can you give it a different name based on the way I've labeled the picture?
X.
It is x, yeah. This side right there is definitely x units long. And the vertical side is y. Do you know any tricks that will allow me to connect those 3 sides?
Yeah, it would be x squared plus y squared equals 1 squared.
And based on the Pythagorean theorem, you just made an equation for the circle. That's what the equation for a circle looks like. It's based on the Pythagorean theorem. Because any point can be turned into a triangle based on the xy coordinates of the point. Now, usually when we talk about equations of graphs, we like to write them as y equals. Remember doing way back in some algebra class? So help me solve this for y, and then we'll ask a graphing calculator to think about it. Some graphing calculators can handle you typing that exactly, but a lot can't. Like, how many of you have experience with the TI type calculators, TI 84s and 5s and 6s and so on? They want you to write it as y equals something. So what's the first step in solving this for y? Not that we have to, we're just kind of for fun. We'll do a little algebra. Want to get
Isolate
y
it
by
on the
itself?
side.
What's that? Get the
Isolate it on the other side.
isolate it. Yeah, yeah. So let's maybe move the x. So how would we move the x if it's connected with addition? Subtract it over to the other side. So then my next line would say that y squared is equal to 1 minus x squared. So the equal sign there.
Which is y equals mx.
Not quite, because we get the square in there. And mx plus b means it would make a straight line. And this line is got the curve of a circle, right? So it's not going to be mx plus b. But, so I don't know what x is yet. There's a lot of different numbers x could be around this. But there's one more step I can do to solve for y here.
Take the square root.
Take the square root. Now that's a little bit tricky, and I'm asking you to think way back to algebra class. So this is where I'm at now. The square root of y squared equals 1, the square root of 1 minus x squared. There's a slight catch to rewriting that one more time. Okay, remember what it is? What do you think? Ashley? No, sorry. No? You just get a snack?
Well, isn't the square root of 1 I? I don't know if that's
No.
important. Oh, it's not okay. I don't know.
It's not that. You have an
Yeah, I
idea?
was thinking you couldn't really get the square root of 1 is 1 times 1 is 1.
Well, the square root of 1 is 1, but I can't simplify this side because the order of operations says the square root is the outer thing. Before I can deal with that, I have to square x, then I have to do the subtraction, then finally I can take the square root. I can't break the square root up there. That's a whole other story we can look at in a minute. So I can't do anything to the right side. What about the left side?
Be y over it.
Almost. There's a slight catch to that problem. So, okay, so I'm thinking of a number. I squared that number and I got 4. What number was I thinking of? No, I was not thinking of 2.
-2.
-2. I was thinking of -2. Okay, so what's the gotcha here then?
Yeah.
It's plus or minus. Anytime you take the square root of a square and you want to simplify it, the problem is the square lost track of what sign the number was. So you always have to adjust on the other side with a plus or a minus, and then the square root. So the next question came back to what Nikki and Ashley were saying is, well, why can't we look at that as the square root of 1 minus the square root of x squared? And I'll just do a simple bit of arithmetic that'll show you why. So consider, earlier I talked about the 3, 4, 5 triangle. So let's say I don't know that 3 squared plus 4 squared is supposed to equal 5 squared. So I'm just going to call it d squared for now. Then I take my square root. So now I have the square root of 3 squared plus 4 squared. And then I say, well, I just would rather take the square root of 3 squared and take the square root of 4 squared. Doesn't that look like a reasonable thing to do? What's the square root of 3? Oh, shit. Yeah, right. Square root of 3 squared. There we go.
It's 3.
It's just 3. Yeah, 3 squared is 9. Square root of 9 is 3. What's the square root of 4 squared? 4. What's 3 plus 4? Does that jive with what we think should happen? No, what's supposed to happen is this says square 3 and square 4, then add them up. That's going to give me 9 plus 16, which is really 25. And when I take the square root of 25, I should get 5, not 7. So something is wrong. Where must the wrong step be? Is the 3, 4, 5 triangle incorrect? Or is this procedure right here incorrect?
Procedure?
Yeah, it turns out this is incorrect. Yeah, the 3, 4, 5 thing is just fine. You can draw that out and see it. The problem is we violated the order of operations. Order of operations basically says the square root, put parentheses around that stuff. Meaning you got to do what's inside first. You can't shortcut that. Once you clean up the inside, then you can take the square root because that's on the outside. We violated the order of operations. We got a wrong answer. So it doesn't work in this simple arithmetic statement. It cannot work in an algebraic statement. So I cannot split it up like that. I'm stuck with that statement. So now I'm going to whip out a graphing calculator and see what the graphing calculator thinks. So Desmos can graph stuff. I don't know if you guys have heard of Desmos. I can't remember if I've used it in here. My favorite tool lately is Geogebra. Actually. And let's look at the classic version. I like this one. So if I type in y equals, now there's no symbol for plus or minus. Computers can't handle that usually. So I just have to start typing square root is SQRT. And then I can say, let's see, does it need parentheses? Nope. What does that look like I just drew? Yeah, it looks like a semicircle. And then if I say put the negative in there, I just have to type it separately. Y equals the opposite of the SQRT of 1 minus x squared. And there's the other half of the circle. So the plus is the top half, the minus is the bottom half. Most computer systems these days are a little more powerful than a TI. And so you can actually type into a lot of them x squared plus y squared, oops, wrong spot, plus y squared equals 1. And then, oh, whoa, that was interesting. It had a little trouble with that. Oh, there it goes. Whoa, that glitched.
Is it because you have all those?
Hello. Whoa, what is it doing? Oh, I know what it's doing. They programmed into it to try and find intersection points when you graph things. And since these are the same curves, it's finding a lot of intersection points and getting a little screwed up. And so there's a little time lag there because it's, oh, I better write to them about that. That's a problem. Maybe, yeah. So here's the whole circle right there. Okay. So that's kind of cool. And it turns out it doesn't matter where the center of the circle is. Pythagorean theorem will still bring you to the equation no matter what, which is kind of nice. So the Pythagorean theorem has lots of applications. There's a lot of wild ways to prove it. Don't speak it out loud. Did anybody find the magic president who found a proof of the Pythagorean theorem no one had ever seen before? One person emailed me so far with the name of that president. Okay, today is the deadline for that extra credit. Yeah, that's extra credit.
Wait, what is it?
Which American president discovered a proof of the Pythagorean theorem that had never been seen before? And send me a little note. Do not disclaim it in class or exclaim it. All right. So we are going to move along unless someone has questions about homework from Pythagorean theorem section. Not at the moment. Okay, I was hoping nobody would have questions right now. I will still take questions next class because I want to play with toys now. So we are going to move into 3D geometry. I posted some new assignments. You should see, if you go to My Lab and Mastering Homework, I put an assignment for 14.3, 4, and 5. They each have 13 questions. And then, let's see, we're going to do activity 8 today. I don't think we'll get to activity 9. We might skip to activity 10, and cool polyhedra is a homework assignment I'll talk about in a little bit. So we're going to play around with some toys, then we're going to do this surface area project. Yes, questions? I will have that tonight. I forgot to post that. I did start putting together one. I just didn't post it yet.
Is it just need to be the president's name?
What?
Does it just need to be the president?
A president.
The guy's name.
Yes, that's correct. Yeah, if you can write down the proof too, that would be even better. Let's see, so final review. We'll post that after class. Okay. Yes.
I was gone the day we got that activity.
So you don't have a copy of it?
Sorry.
Okay. I don't know if the blank comes with me. Just have my copy. I will get you one in minutes. What's that?
I just take notes.
Yeah, I can. There's one on the top of the page here.
Okay.
That you could print, or I can just print it for you now. Oops. All right, I'll find the printer in a second. Okay, so I'm going to stop this video here and restart it in a little bit. What I need you all to do